Hello. Hello. Am I audible?
Yes, sir.
Hello.
Yes, sir.
Yes.
Okay. Thank you. So, you guys have any feedback on the class on the previous session?
Uh,
Anything that? Yes. Yes. Please go ahead. Yeah.
Sir, actually, the idea related to the machine learning and artificial intelligence, we would like to know about the from the basics of that. Means
Okay.
how the idea was established and how it was evolved, and what is this mathematics or the science behind it, so that we
Okay. Yeah.
can
Yeah. So.
catch the step by step.
Yeah. 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 I got it. I got it. So. Yeah. I prepared some slides on that only today, and so yeah, I'll try to add more on that. Anything else? Any other comments, feedbacks that others have? Uh, you guys have, if you have no comments, I will start with the today's session. So just let me know if any kind of technical difficulty comes. And so in the previous class, we had seen different things such as the chart of neural networks, and I try to give an overview of what the different uh, developments were in the field of AI and machine learning, and going from starting from giving trying to give an overview of what constitutes a data scientist today to applied scientist, and the pathway for deep learning. And so previous class was kind of an introductory class. I'll try to go more into mathematics of machine learning, and what the way I have thought about this course from now on, from this session, is that I will take the first, divide it into two halves, so we can have a 5 minute break, and we'll cover theory in the first session and some form of hands-on in the second part. So that is purely optional. If any of you feel that it is if any of you feel that it is becoming too much, or for that day it's an overload or too much material, feel free to leave in the session 2 if you want. But I would highly recommend you to be there in the second session as well. So now we'll talk about mathematics for machine learning. If you want to basically have a in-depth understanding of the mathematics of deep machine learning, so you have to understand one thing, that deep learning is a type of artificial intelligence, and artificial intelligence is the bigger, you can call it as a superset, and machine learning is a part of it. Then we have reinforcement learning, which is kind of machine learning, but it developed parallelly with machine learning, and these days uses a lot of machine learning, basically deep learning algorithms at its core. But artificial intelligence is the bigger set. Then comes machine learning, and this book is a very good uh, it's a very good resource. You can consider it to be a comprehensive end-to-end material on different on the basics that would be required for you to understand the concepts in machine learning or artificial intelligence. So machine learning is standing on different pillars of regression, dimensionality reduction, density estimation, and classification. So regression is like the task. Okay, so it can be linear regression, multivariate regression, basically linear, an extension of linear regression, or it can be using some other form of approximation. So if we say y is equal to fx, where f is the transformation, so x is your independent variable, y is your dependent variable. So f can be anything. You can use support vector machines, you can use decision trees, you can use different form of decision trees like random forest, and all these components, they are basically the foundation of these components lies in linear algebra, vector calculus, analytic geometry, probability and distributions, matrix decomposition. So I like to think of matrices and do a sophisticated linear regression, as if you would like to say that, to estimate the weights or to develop the model for which is better than linear regression, because in the real world the phenomena are not linear, it is non-linear. But again, so if a problem requires you to, if a problem requires you to not use, like if linear regression is enough for a problem, then going to complex algorithms is an overkill. So as I said in the previous class. Now, very, like, I just have a couple of slides on the mathematics of machine learning for this class, but I would be covering. So there is a deep learning specialization on Coursera. You can go to it, you can see it, or you can do it at your own. So this is a specialization consisting of 5 courses, which provide an in-depth knowledge into what are neural networks and deep learning. How would you improve deep neural networks? Then after you know how to run the deep learning models, how would you structure the machine learning projects, and then 2 specific types of examples. So course 4 and course 5. Course 4 is on convolution neural networks, and course 5 on sequence models. Sequence models is nothing but something like time series data sets that we have in our field or in any other field like finance. So those are in natural language processing. They have a sequence of words which are related to each other. So the fundamental, the basic building block for in the machine learning are geometric vectors. So you if x, so vector is basically having a value, so it's having a magnitude and a direction. So you can do various operations, like you can sum the vectors. Then you have polynomials. So polynomials are basically continuous functions which span across the so which have values for every point in the x dimension. Then this is a mind map of the basics of mathematics that you would require for machine learning. I would not go into the details right now. This book is a reference material for the mathematics of machine learning. You can do various things, like you have 2 straight lines. If you want to find out solution, you can find it out using by solving these 2 equations, or you can graphically plot them, and the intersection of these 2 lines provides you a solution. So also, you would have seen in, if you guys are also doing the Python course, so there is a function reshape. So if you have a 4 cross 2 matrix, if you reshape or you flatten that matrix, so how would that actually get flattened? It's very important to understand that. So if you flatten it, the second column gets appended, or the second, it gets appended below the first column, and just it comes out as a vector. And then we have the matrix multiplications. So you can have this blue matrix multiplied with the yellow, and so you can see and or you can have in it in the inverse manner. So this is a 3 cross 2 matrix multiplied with a so a 2 cross 3 matrix multiplied with a 3 cross 2 matrix. So the output will be a 2 cross 2 matrix. So these are some of the things that I thought I'll put in this session. Then I was talking about reinforcement learning. I think I ended at reinforcement learning in the last session. So in reinforcement learning, you basically have you have an agent. So an agent it's like you are playing a game. Okay, so you are playing a game of football, or you are playing some other game, and then you are interacting with the environment. The environment has got some rules, like for example gravity. For example, there can be a single agent, or there can be multiple agents. Now, based upon the action that you take, maybe the type of kick you give to the football, the environment will give you a reward, which can be a positive reward or a negative reward. You can do a self goal, or you can do an actual goal, and then based upon the your action, the environment is giving you the reward. Then the state of the environment changes, which is given back to the agent. So let's say maybe the number of goals it increases, and then the agent further tries to optimize or maximize the reward, play in such a fashion that it will try to maximize the reward. So the agent previously, prior to deep learning, people used to use very simplistic statistical approximations. But after deep learning, if you what they started using was a deep neural network. So as an agent in a reinforcement learning framework, and the new field of deep reinforcement learning developed. So it's a very interesting paradigm which you should be aware of. Then I would be covering some very popular deep learning or architectures of the models which are powering the devices of today, or the research, or which are I would say have led to this kind of an explosive growth in the field of artificial intelligence and machine learning. So the first is transformers. As you can see from its name, they have named it similar to the Transformers movie. Now, in 2017, a paper came. It's called "Attention is All You Need," and that work outlined that the architecture that they proposed used some form of matrix multiplications, which the authors called as attention mechanisms, and it's a form of an encoder, decoder, and recurrent neural network. So the first paper, which is "Attention is All You Need," I will maybe just show you that uh, that that paper has become really popular. Now you can see around 37,000 citations, and the base this paper basically talked about attention in a sequential data form. So on sequential problems like NLP, wherein you have the input in, let's say, English, and you want the output in another language. You can have different types of tasks. So I yeah, we don't have the that here. Okay, so in this mechanism, so in this attention based framework, this is the building block of the transformer model, which was initially proposed for the NLP problems. But now transformer is being used for computer vision problems. If you have spatial data for time series problems, so in general time series applications, and it has basically moved into almost all the devices that we use today. So this is a very important thing to understand. It's slightly complicated, but I would suggest you to go through it after the class or whenever you get time, because transformers are showing really great performance as compared to the deep neural networks, which became popular somewhere after 2010 or 2014. Then what we have is generative adversarial networks. Now, generative adversarial networks became so they were proposed in 2014, and their primary use was for image synthesis. And generative adversarial networks were in its pure form. It basically deals with, you can consider it to be an unsupervised learning algorithm. And in a GAN, so it's popularly known as GAN. In a GAN, we basically have two models. So one is known as the generator, then we have the discriminator. So what a GAN does is basically create samples. So you have a distribution of data, right? And it will create samples from the distribution, which which are not present in the data, but which are realistic enough. So one example for this is, there is a website, this person does not exist.com. Now, yeah, so if you go to this website, this person does not exist.com, they have basically trained a GAN. This was a typical GAN, like the traditional GAN, which which was initially proposed. Now different types of GANs have come. So they trained the GAN with the available all the available image data sets of humans. And what they were able to do was generate images which look realistic, but which are not in the original data set. So they say that this person does not exist, this person has never existed, and the GAN algorithm is running in the background. And if you just keep on doing refresh image, it will show you new people, which these people have never existed before. So this can be, like, you will discuss on how this can be useful, but I will very briefly discuss into talk about what a GAN does. So it will take a random input. You can think of a random number generator. So you can generate some random number, let's say from 0 to 1. It can be a float, and which goes as an input to the generator. Now the output of the generator is, for example, an image of the data set that you have collected, or you can consider it to be anything like weather. Okay, so the spatial map of rainfall can be anything. Now, after the generator, so initially the generator has got random weights, and it will generate a very bad looking image. And what we do is we label this sample as 0, and then you have the real images. So the real image you label as 1. Now these inputs with the real image labeled as 1, the generated image labeled as 0, you pass to a discriminator. So you train a discriminator, and you are telling you are passing the two images. One is the generated image, one is the real image, and the corresponding label of the real image is 1. The corresponding label of the generated image is 0. Discriminator, you are teaching the discriminator. So discriminator is also a convolution neural network, is taking an input as an image, and it is outputting a class, let's say 0 and 1, whether the image is real or it is fake. And you are giving it a labeled data set. So you first train the discriminator, then you train the generator and discriminator both. The discriminator tries to fool the generator tries to fool the discriminator. What they were able to see was that this performs better than any. So other for other use cases, which we will discuss later, GANs are really effective in improving the accuracies or making the mapping function. So that's about GANs. Then we have an algorithm known as k-means clustering. So if you have k-means clustering is basically a clustering algorithm. It's an unsupervised learning algorithm, and it seeks to categorize the data using the density estimation. You have to choose the value of k. So that is a parameter that you have to take care about. But so if you give, for example, to this data set, which is in two dimensions, x and y, and you just plot this data set, I mean, we can see that it's approximately it's having three clusters, but you can choose any number of clusters. So if you give the k as 3, so first it will randomly assign the centroids of the clusters. So it will randomly assign those centroids, and then it will start computing the distance of each point from those centroids, and keep on updating the data points which are corresponding to a particular cluster. So you keep doing that until you converge, and until there is no change or you don't get any change in the points which are getting added or deleted to a particular cluster, and you can cluster your data using this k means clustering algorithm. Then there is another algorithm known as k nearest neighbors. So k nearest neighbors is basically a supervised learning algorithm, which was first proposed in 1951. And in k-means clustering, so for example, if you have the different flowers, right? So you can have the variables or the precursors as sepal length, sepal width, and based corresponding to the sepal length and sepal width, you have the type of the flower, whether it is centosa or it is virginica. So you have this as a multi-class classification problem, and you know the values of the precursors, and you're trying to basically do find out the or develop a model such that if you choose any point in this state space, that point should be classified as a particular flower. So a lot of times people confuse between k-means clustering and k-nearest neighbors. So that is why I thought about putting both of them in a same slide. Now, yeah, so we have policy. So this is, I will just skip this. This is about the reinforcement learning algorithm. And so we'll take it up when we talk about the reinforcement learning algorithm. And then there is a very important concept of regularization in machine learning. So what is regularization? You can see the first plot. So if you can see this underfitting plot, the data set is are the blue scatter plots, and my model is the red line. So in this case, we can see that the model is underfitting. It's not generalizing to the data. Now on the in the middle is the model which is just right. So which is what we would ideally want. And the third or the rightmost figure shows a model which is passing through each point in the training data. So this model is overfitting. Now, what do we mean by overfitting? So when we have to develop a machine learning model, you first divide your data into training and testing. So typically people would use 80% of the data as training and 20% as testing. And there are different types, different methods by which you can divide the data into training and testing. So there is something known as k-fold cross validation, wherein you would first consider the first percent 20% data as testing. Then in the second step, you would consider the data from 20% to 40% as testing, then 40 to 60, then 60 to 80, and then 80 to 100%. So you would run the model 5 times so as to ascertain that your results are robust. Now, if you are using a complex model, you are likely to end up overfitting your training data set, and the technique used to avoid overfitting is known as regularization. What we typically do in regularization is that you add, so we saw in the previous class that you build a model which will output you a y hat, and then you compute the error term, which is L2 norm or L1 norm between y hat and y, and you compute this error term. So in the regularization, so if you are doing regularization, you would also add this term to the loss function. So you would say plus lambda and summation of all the weights. So what you're doing is, if you are having more weights, that means you are having more parameters. So sometimes you can even consider randomly, or you can thoughtfully try to take the parameter. You can build precursors like x square, x cube, or x1 x2. So if you have two variables, you can have x1 x2, x1 square, x2. You are increasing your the size of your precursor, so the number of weights will increase. So you are penalizing your model based on that. So you're adding that as in the loss function. So this lambda parameter is known as the regularization parameter. You can also in an L1 norm. So if you are calculating loss as an L1 norm, so you would say lambda and summation of the modulus of beta I. So this is one. And then the second type of regularization is you do data augmentation. So you can basically do some kind of transformations to the data, like randomly cropping, dilating, or rotating the data set, adding some amount of noise. Or you can use k-fold cross validation. So you, just like I discussed, you can divide the data into k groups, train on k minus 1 groups, and test on the one group. Try all the k possible combinations. Then you have the concept of like how you can also change your approach for training. You can add random noise to the weights when they are being learned, or you can use something known as dropout. Now, what dropout is basically, so you have, let's say, this is your this is your original network, and at the time of training you say that your dropout is 0.3 or 30%. Then dropout, basically what it does is it would switch off some of the connections of your network. So in this case, you have, so the original network, let's say, has 16 connections. So this network has a 30% dropout rate, so it has got 11 connections. And this type of regularization is very popular using dropout. Then comes the another very important aspect of imbalanced data. In If you are doing a classification for a classification problem, or even for a regression problem, let's say you are working on some kind of extremes. Now extreme events, they don't happen always, right? For example, lightning, or for example, floods. So you are having some kind of input data set, which, so a continuous data set of temperature, pressure, but you are having these extreme events for which the data is also very rare. I mean, very rarely these kind of events will happen, but you are trying to build a model in which you would simply give these the variables. You have precursors or inputs, and then you are trying to model the extreme events. So for that case, what we typically do is, we the way we compute performance of the model is changed. So different types of metrics, like precision. So precision is true prediction divided by true prediction, or true positive divided by true positive plus false positive. Or you compute the F1 score. So F1 score is 2 times precision into recall by precision plus recall. So you, rather than taking a simplistic loss function or computing the accuracy in a simplistic manner, the best case is to change the performance metric in case of an imbalanced data set. Also, other possible solutions are, so you can replicate the available data until the number of samples are comparable. So you can basically choose from the data set, and you can keep equal number of samples of, let's say, lightning, and equal number of samples of no lightning events. You can use synthetic data set. You can modify the loss to reflect greater error when misclassifying smaller sample set, or you can basically change the algorithm. So another possible, like another thing which people have seen while as a trick of the trade is, if you're using a deep neural network, then you don't train for large number of epochs. That would actually overfit your model. Then comes the concept of principal component analysis. I would not go into too much detail, but I think you will study this in your statistics course also. So principal component analysis is used for dimensionality reduction. If you have a lot of variables in the data set, for example, the scatter plot showing the blue data points. Now on the x-axis is your feature 2, y-axis is your feature 1. You can see that this dataset doesn't require two dimensions. So it can be plotted on a, if you use this new feature 2, that's enough. You just need one dimension. So principal component analysis, I would not go into explaining the algorithm. You can see this later. So principal component analysis, and there is another algorithm known as TSNE. So we'll cover that, which is also popular in the machine learning community. Then comes the concept of ensemble learning. So just a second, I'll have water. So in ensemble learning, we basically have different techniques like bagging. So what is, first of all, ensemble learning? You train different models or learners, and you combine weak models or learners into one predictive model. To so you basically have a lot of different models, or you have similar model, but you have trained it separately, and then you are trying to combine the results of all these models which are weak into a model which is robust and very strong. So one technique is, so the first one is known as bagging. So in bagging, you train n different weak models, or which are usually of the same type, with non-overlapping subset of input data set in parallel. So at the same time, you have n non-overlapping input data sets, and you train the same model. So you train it n times, so n data sets, n subset of data sets, and n models which are homogeneous. And in the test phase, so each you evaluate each model. And what you do is, so let's say you are using a random forest, and so what you do is you divide your data set into 10 groups, or 10 subsets, and you then train 10 different random forest on these 10 subgroups. Now, at the time of prediction, so you would have a test data set or the input, which you would provide to each of these 10 models or n models, and then you would use voting. So for example, if the model is predicting 0 or 1, so you would use voting to select the prediction. So maximum, whatever gets the maximum number of votes wins. So that is found to basically perform better than training just one random forest. Then a second type of method, ensemble learning method, is called as boosting. In boosting, you train n different weak models. So usually which are of the same type. So what we mean by this is, like, for example, you are using neural networks. So you can change the number of layers, or you can change the number of nodes in a particular layer, and with the complete data set in sequential order. So you would basically train the first model, and then on the data set, and then you would again train on a different model, but in a sequential manner, so that you are basically aggregating on the accuracy. So So that is boosting. And then we have stacking. So stacking is similar to boosting. So in stacking, you would train n different weak models with one or two subsets of dataset in parallel. Once the weak learners are trained, they are used to train a meta learner to combine predictions and carry out the final prediction using the other subset. So in test phase, each model predicts its label. These labels are fed to the meta learner, which generates the final prediction. So this is like in stacking, you would have n different models which are trained on which are trained which are trained parallelly, and then you would have a meta learner. So it's like if you can have one model as support vector machine, another model as random forest, another model neural network model, or different neural network models, and then you can assign weights to these models, and you can create a meta learner which will basically do your final prediction. So that is known as stacking. Then the different types of algorithms. So machine learning algorithms. So we have seen linear regression for regression problems, fitting a straight line to your data set. Then we have logistic regression for classification problems. Then we have the decision tree, random forest, and then we have an algorithm known as gradient boosting. So gradient boosting is basically used on decision trees, and it uses the boosting part of the ensembling methods. Then we have the neural networks. And so there is another type of algorithm. It's known as collaborative filtering. So in collaborative filtering, what happens is that, for example, you have a problem of movie rating. So you have a number of users and you have a number of movies. Okay. So you have the users on one axis, and you have the items. So for example, the movies, and in this matrix corresponds to what is the rating that each user has given to a movie. Now this algorithm is basically used by almost all the e-commerce platforms like Amazon to show you the suggestions of different products. So how they would do that is basically each user, they assume that each user is a vector. So we basically use an embedding vector for each user, and we use an embedding vector for the movie. So let's say the size of the embedding vector you would have to choose on your own. And what you would typically do is what you would typically do is you would have a big matrix here on the left for the which is the embedding matrix for the users. So each user can have a different taste. Like they are of a certain personality, they are from a particular region. So and they have the language preferences, and each movie has got different genres. So depending, so the embedding, that's what will the embedding vector represent. So each movie can be a thriller movie, a horror movie, an action movie. So for example, if you have three different types or genres of movie, then you can have the size of the embedding vector for each movie as 3. Now the problem is, if you have a new user in the if you have new user, and you want to predict what type of movie to recommend to this user. So that is where comes the like the this algorithm. Basically what it does is, with the existing data set of the users and items, it would multiply the two embedding matrices, and it would generate the data set, the matrix for the rating. And the initial values of the embedding matrices, they are considered as. So I think this is maybe, if you guys feel that this is getting difficult, or uh, difficult to understand, let me know. But I think this is getting difficult, so I would explain you collaborative filtering, yeah, using this example. Oh, this is not. Yeah. So you basically have, okay. Sorry, I think I opened the wrong one. Yeah, this one. So by the way, this course, Fast by Jeremy Howard on Fast AI, it's a series of 20, around more than 20 lectures, which are of 2 hours long. And this is a very good course if you want to do deep learning, hands-on or applied deep learning. So okay. So this is what I was explaining. Let's say you have the users. Am I going fine? Is everybody with me? Is there any question? No. Am I audible?
Yes, sir. You are going fine.
Okay, fine. Thanks. So let's say you have the different users. So you have the user ID as 27, 49, 57, 72. So these are your users. And then you have the movie IDs. Okay. So now each movie, so this is corresponding, each row here corresponds to a movie, and each column here corresponds to a user. So this is the rating, for example, that the user, so this is basically normalized, but this is the rating that the user 27 has given to movie 14. 1.44 is what 27 has given to the movie 29. Now what you do is you assume that the users are represented by a vector of dimension 1 2 3 4 5, of dimension 5, and the movie also can be represented by a vector which is of dimension 5. So each movie is a vector, is basically a number, or is a vector, and each user is also a vector. Now to get this number 0.91, what you would do is you will multiply the vector corresponding to the movie 14 with the vector corresponding to the user 27. Now initially, so you would ask, how would you know to begin with what would be the values of these numbers? So you would not know. So what you would do is you would assume, you would randomly initialize these numbers, and randomly also initialize the embedding matrix of the users, and you would compute, so you are developing a model. You would multiply this matrix with this matrix to compute a corresponding matrix of the reviews. Okay. And then you have a model generated value and you have a ground truth. Then you would compute an error function, and you can, so in a very simplistic manner, you can keep updating the values of these numbers and these numbers and try to minimize the error. So this algorithm is known as collaborative filtering. It can be used for any different type of other application. So you have, you have rainfall, or you have the you have, so you can have different types of events, and which correspond to the users, and or you can have the something else which is corresponding to the movie ID. Now how would you entertain a new user? So that is where people will collect the data set. So for example, these websites will collect the your age, so when you are signing up for their account, they will collect some data set, and they will have a predictive model which basically estimates and compares you to the existing users, and then they will give you suggestions based upon their estimates of how you will rate a particular movie. And that's how a new movie is also used to show as a potential recommendation to the different users. Now this is a very simplistic matrix multiplication problem, or the algorithm we are calling as collaborative filtering. This can be transformed. So let me see if Jeremy shows that. This can be transformed into a very easy deep learning problem, wherein you can have the different inputs of the users, the embedding vectors of the users and embedding vectors of the movie as an input to a deep learning model, and you can try to estimate the reviews. So in the input you can have a combination of the embedding vectors of the users and the movies, and in the output of the deep neural network you can have the rating or the review for the movie. So you can use this or tune this for your own application. So this was about the collaborative filtering algorithm. Then I have put some different cheat sheets for the libraries which are very important while so when you doing data science or machine learning. So Numpy, which you are already learning in Python, is very extensively used. So you should know that. So this is an example of a 1D array. This is a 2D array. Now we have a 3D array having 3 axes or 3 dimensions. So the way you would create an array is using np.array, and then you would use np.zeros, np.ones. So np.zeros 3, 4 will create a matrix of size 3 by 4, and all of them are filled with zeros. Np.ones will create a matrix of size. So as many commas you give, or as many numbers you give separated by commas, that many axes or that many dimensions of the matrix the NumPy will make. And so this will make a 2 cross 3 cross 4 matrix, which are all filled with ones. Then we have np.arrange. So np.arrange is, if you say np.arrange 10, 25, 5. So this will have create numbers 10, 15, 20, 25. And then we have np.linspace. So what np.linspace will do is it will create, I think, 9 numbers. The first one starting from 0, the ending at 2. And then you have random number generator. So this will generate a 2 cross 2 random number matrix. If you want to save your array, so you can say np.save. You give the name of the file in a string, and then you give comma the name of the variable. If you want to load that file, you say np.load text, the name of the file, or you say if it is separated by commas or another delimiter, so you say np.gen from text. You say some file name in string, and the delimiter you'd have to give. The data types in NumPy are integer, float, complex boolean, object, string, Unicode. Then you can inspect your array using a.shape if your array is shape. Then what is the length of your array or list? So you give length, len, which is the keyword, the number of dimensions, the size, the data type. And if you want to do type casting, or you want to change the type of a data type, so you can say dot as type, and in the bracket you give the data type that you want to convert your array to. So you convert B as an integer array. Now there are different arithmetic operations that you would do in NumPy. So plus, minus, divide, multiply, and you can also use their functions which are much faster. So np.multiply, np.exp, np.square root. So I will not go into further details of this. You can look at this on your own. And then we have the machine learning library in which is the most simplest machine learning library in Python. It's called Scikit Learn. Scikit Learn has got various algorithms which you can use. So from linear regression, support vector machine, naive bayes, k nearest neighbors. So we just discussed k nearest neighbors, and k means clustering. So you can use k means clustering to cluster your data, and principal component analysis to basically decompose your or do dimensionality reduction. You can do supervised learning or an unsupervised learning. So a typical function or which is used in machine learning and deep learning is called as fit. So you would say if LR is your model, then you would say LR dot fit x comma y, where x is your input, y is your target. And you can do similarly for k nearest neighbor support vector classification. So the way you would extract the model, so let's say if you want a linear model, so you would say from sklearn dot linear underscore model. So linear underscore model is a class in sklearn. Sklearn is a short form for scikit-learn, and that is what is being used in the code. You would say import linear regression, and then you would, so linear regression is a class, and you would then make an object of the class. You would say LR equal to linear regression, normalize equal to true. So it will automatically normalize your data sets as well. And then you can say LR dot fit x comma y. So there are different features of sklearn. So you can load your data using NumPy. Then you can do train test split. So the function is from the class cross validation in sklearn. It is called train underscore test underscore split. And you would have to also specify, I think, what is the percentage of the test data that you want. Then they have a pre-processing module. So in the pre-processing module, you can do standardization. So you can say, so from sklearn.preprocessing import standard scalar, and then you can say scalar. So scalar is the object you create from standard scalar class. You say dot fit x train, and then you transform. So standardized x is, you say, transform it to to uh, to so you basically standardize the data set. I'll have to see what is the difference between standardization and normalization. Should be similar, but the idea is to basically, so if you want to fit your data to a model, you should basically bring your data from to in the range from 0 to 1 or -1 to 1. So that is the idea behind pre-processing the data set. And then if you have a classification problem, then you would use the binarizer. So binarizer will basically binarize the data. So you can use a threshold. So the threshold is 0, below that and above that. So it will transform the data into binary numbers. And then we have the pre-processing functions for imputing missing values. So you have different strategies, like you can say mean or median, because you would have to take care of the pre-processing. Your data should not have any nans. And then you can generate polynomial functions. So you can say from sklearn.preprocessing import polynomial features. This will, and you make 5 such polynomial features. So you say you have x square, x cube, x to the power 4, x to the power 5. And then if your sklearn has different classification metrics like accuracy score, so you compute the accuracy, the number of so you have the test y underscore test is your actual ground truth test data, y underscore pred is the model predictions. So you would compute how many, so if let's say in a classification problem, how many percentage were correctly classified. And then you can also make a confusion matrix. So confusion matrix is when we were seeing, yeah. So this is your confusion matrix: true positive, false negative, true negative. So sklearn can also make your confusion matrix. And you can compute your mean absolute error, mean squared error, R2 square. This you would have seen from your statistics class. And then you can do cross validation. And the final thing is, so if once you have trained your model, so what you can do is, so the parameters, so there are a lot of parameters that you have to use in your model. For example, if you are having, yeah, if you are having using k nearest neighbors, so you don't know, right, from the beginning what is the n underscore neighbors parameters. So you would basically make a grid of these hyperparameters, and sklearn has got this grid search. So there are different methods to tune the model. So grid search is like brute force, and it's an old strategy, but just like very simply you can search over all the permutations and combinations of the hyperparameters, and you would have to create a grid object of the class grid search cv, and then you say grid.fit xtrain comma ytrain. This will print, you can also print the best score and the best estimator. So this will give the best estimator dot n underscore neighbors. So you would have to define this, what are the parameters on which you are trying to tune the model, and then this will give you the best optimizer or the best parameter for the for your model. Then you also have something known as randomized search. So in randomized search, so in grid search, what might happen is that you might be using a lot of computational resources, and you would try to go and see at all the possible combinations. Let's say np.1, comma see at 1 and 2, but then you can also use random search. So the model will so the way it will train is that it will randomly search at different combinations of the hyperparameters. And what this will do is, so randomized search, so a typical strategy that people would use is that initially you use randomized search, and then once you have got some values of the hyperparameters, then around those hyperparameters, if you use a grid search, then you can reach a global minima in your loss function. So then, yeah, so this cheat sheet is on SciPy, which is the scientific Python library. Not go into this one. And then we have the matplotlib, which is for visualization that you must be seeing in your Python class. And yeah, I'll skip this one as well. Yeah, so then comes Keras. So Keras we will see in detail in our hands-on session. I will try to see today. Now I have covered like a very brief overview that I thought like last class I will cover, and just now so from now on I will show some examples of applications in the geospatial datasets, and then move on to the real part, the details. So in the geospatial Python or data science ecosystem, there are various tools for analyzing QGIS, PySal, GeoDA. Then for visualization, these are like the most advanced tools. And then so the non-geospatial data science tools, you can see Scikit Learn, XGBoost. Jupyter is the platform to do these data science tasks. And then we have the Pandas library to handle the tabular data sets. Then we have the two big deep learning libraries, which are, so PyTorch is from Facebook, TensorFlow from Google, and then we have Matplotlib for visualization. So then this is like I will show you some examples of how people are using deep learning for weather forecasting. So this is one of the example, and graph neural networks is becoming very popular these days. It is outperforming a lot of the previous or older models. And in this study, what they do is they take a lot of variables from era 5 dataset, and they keep the era 5 and machine learning model side by side, and see that the machine learning model using graph neural network is performing in a similar manner as the original era 5 reanalysis, which is the ground truth here. Then we have another work in which is called ForecastNet. It's a global data driven high resolution. So they use something called as adaptive Fourier neural operators. And then there is another work which is called as a Bayesian deep learning approach to near-term climate prediction. So when you encounter the term Bayesian deep learning, it might sound too complex or difficult to understand, but it is like the more difficult it sounds, the easier it is. Bayesian deep learning is basically you are developing a lot of different models, and you are also computing the uncertainty values. Or so let's say you are developing 20 or 50 deep learning models, and then you are coming out with a distribution, and from that distribution you are talking about prediction which is happening most of the times, or you are looking at the different metrics of that distribution. So that's just about it. So that's just about Bayesian deep learning. And then there has been a recent example on using generative adversarial networks, that is GANs, that I was talking about. So this study has used GANs to simulate weather, which is looking similar to the ground truth or error 5 reanalysis. Then comes so I'm talking about like the fundamental type of works which are using different data science algorithms in geoscience applications or in weather and atmospheric sciences. Then there is this study which basically uses they transform the spherical data set in a so you have the spherical data set in latitude longitude grid. They transform it in a cube sphere format. And so cube sphere is basically a cubical sphere having 4 faces along the tropics, 2 along the poles. And so the problem is that on doing convolution on a sphere is that the libraries PyTorch and TensorFlow, they were basically developed for 2D computer vision problems. Now to do that, to do a spherical convolution requires you to build your own library, which the big software development teams of Google and Facebook have worked for years to develop. And you would have to use CUDA so as to enable the computations on GPUs. So that's what they like. So these people, they come up with an alternative of transforming the spherical data into a cube sphere, and then each face of a cube is considered as an image, and an input as an image and an output. They output an image and basically use a convolution neural network, which is also called as a UNet. So this is the UNet architecture of a convolution neural network. So we were seeing yesterday the different architectures of CNNs like AlexNet, LeNet, ResNet. So this is UNet is a very popular algorithm for image to image regression. So it can preserve your 2D patterns in the data. Then comes another paradigm. It's called as reservoir computing. In reservoir computing, what you have is a big reservoir. So you can think of this as some kind of a big bag which has got a lot of different neurons. Now these neurons are not trained. So these are not trained. The green ones are not trained. What is trained is the output. So these arrows, each arrow corresponds to a weight. These are trained, but inside these this is not trained. So you have some kind of non-linearity in the model itself, and this is basically able to represent the chaotic systems really well. So people have used this link is not working. Yeah, so people have tried to use reservoir computing for simulating the Lorentz system or for financial time series, which are quite difficult problems to begin with. And I think this is, yeah. anyways, yeah, so you can see this paper at your end. And then comes, so these were some examples of the applications of data science within the geoscience field. And then comes a very important component, which is known as explainable AI. So what is explainable AI? It is basically, so when artificial intelligence and machine learning was developing in the somewhere around 2015 2016, a lot of people had their doubts about these models. As in, so the biggest criticism of these models was that they are a black box. So how can you tell, how can you explain what is happening within the model? So now there are libraries, or there are techniques which can help you explain these models. You can tell what is happening inside the model, and that comes under the ambit of explainable AI. So you can tell how faithful is your model, whether it is robust, whether it is complex, whether it is, what is the randomization in it, what is the localization in it. So a very popular paper, which talk you should know about, and which laid the foundation of explainable AI. It's called as Zeiler and yeah. So, oh yeah, there was a typo in that. So yeah, that's this paper. It's called Visualizing and, oh, this will take some time to load. So this is called as Visualizing and Understanding Convolutional Networks. So yeah, I will go to this one. Okay. So as you can see in this figure, yeah, so this is the crux of this paper. So for example, you are having an image classification task wherein you have the images of people, okay, and you are trying to predict the classes, or you are trying to say what they are. So what these guys like Zeiler and Fergus, they showed in 2013 was that the initial layers, or the, so you have a deep, if you have more than one hidden layer, that network is known as a deep neural network. And in a convolution neural network, so if you increase the number of layers, you are increasing the non-linearity of your model, or the complexity of your model. So they plotted, what they did was they plotted the values of the weights of the layers, and they found that the first layer, the initial layers, they correspond to the features which are more or less linear. So they are trying to understand the different type of edges in the data set. Now the layer 2, when they plotted that, they found that it is basically trying to look at some kind of simplistic curves. So you can see the different weights. So this is like the different 3x3 weight matrices. So these weights are trying to look at the simplistic curves. And when they try to visualize the layers, let's say the layer 3, which might be one of the last layers, so the weights were more or less similar to the faces of the people. So what the model is trying to do is, it's basically trying to unwrap your non-linearities and trying to create features on its own, and generalizing for that particular task. But you can typically remove the last layer from a network and use it to another problem, which is very popularly known as transfer learning. So this paper is for like anybody who comes to criticize deep learning. Like, I would suggest you guys also to show this paper. And so that's about explainable AI. And it is already 3:14 now. So I will try to cover one hands-on example today, and maybe close this class. If you guys, if this is becoming too much, you guys are free to free to leave, whoever is like if having further commitments, but I will cover an example for using Keras. And so what I'm using here is called Google Collab. What I was this is the platform I was discussing on day one about. So this is from Google, and it is a notebook as a service. So Jupyter notebook as a service. So you don't need to basically now, so for at least for some level of complexity or tasks, you don't need to set up Python or stuff in your machine. You can just run collab.research.google.com, and this comes with a set of pre-installed libraries, and you can go there, open a new notebook, or this is, yeah, so you can go there and open a new notebook or use somebody else's work. So what we are talking about today is, so in this hands-on session, is image classification from scratch. And the data set is an image classifier, so the Kaggle cats and dogs data set. Now this example, they say, shows how to do image classification from scratch, starting from JPEG image files on disk without leveraging pre-trained weights or a pre-made Keras application model. So Keras is okay. So there are two main libraries. One is PyTorch and one is TensorFlow. And Keras is a kind of wrapper over the TensorFlow functions. If you have to write a TensorFlow code from scratch, it requires lots of, you will have a lots of code there, but Keras can do things for you by abstraction, by hiding a lot of things. And for application purposes, for doing stuff in a shallow manner, Keras is good enough. And Keras now comes as from TensorFlow version 2.0. It comes as a part of TensorFlow. So for those of you who are seeing Google Colab for the first time, you would typically run a cell in the Google Colab in a similar manner as you would run in a Jupyter notebook. So you would press a shift and an enter, and you have options for code and for text. So this is a code cell, this is a text cell, and then you can choose from runtime. So okay, so they have option to for a GPU or a TPU here. So we will change to a GPU, and we will change to a high RAM. And every account gets access to Collab for free, and you can access this GPU, which is a 16 GB Tesla P100 that they are offering for free. But the only, okay, yeah. Yeah, but the only problem is, yeah, so the only problem with this is that if your dataset size increases, then you are limited by the, so you can connect this through Google Drive. So if your dataset size increases, you are limited by the 15 GB limit on Google Drive that you get for free. So you would have to either increase it or run it on your own system. So we will download the dataset, Kaggle dogs and cats dataset. So you can see we are getting a very high speed because this is running on their server. And now we are unzipping. So this is the file Kaggle dogs and cats.zip. So we are unzipping this zip folder, and this gives us the folder pet images. So let us see what is there in the pet images. So we have cat, we have dog, and what is further there. So if you have to run any terminal command, you can use an exclamation inside Google Colab. So let us see what is there in cats and dogs. So Yeah, so you see you have got these images, the JPEG images, and now so they are saying when working with lots of real world image data, corrupted images are a common occurrence. Let's filter out badly encoded images that do not feature the string JFIF in their header. So they are saying that they will remove the corrupted images. So what they do is they will loop over the folder cat and dog, and then the folder path is pet images and then cat or dog, and then go to file name in. So you create a list of the files in this folder path, and then the file path you give the absolute. So you have to give the absolute path of your file for your files in Collab, and then you try to open it, try to open the file, and you say if object equal to open if path comma rb. So is it JFIF? So I think this JFIF is a standard, some kind of convention if the file should be as JFIF encoded. And if it is, so you finally close this, and if it is not, so if not is JFIF, so this will break, this is underscore JFIF. This will either return a 0 or a 1. And you say if it is not JFIF, then you remove fpath, so you remove that file. So let us see how many images. Okay, so they're saying 1500 files were corrupted. And then we say, okay, so they already know that the image size is 180 by 180. We are taking a batch size of 32. I will come to what a batch size is. And then you have a trained data set. So you say TF. So we have said, so TF is basically TensorFlow. So we have said here import TensorFlow as TF. And also we have said from TensorFlow we have imported Keras, and from TensorFlow.keras we have imported layers. Yeah, so there is this function inside Keras preprocessing. So we say tf.keras.preprocessing, and we get this function image dataset from directory. And the first argument you have to give is the name of the folder where these images are. The validation split that you're giving is 0.2. So what we mean by validation split is, so at the time of training, so I was talking about the training and testing data. So you typically have, let's say 20% of test data, 80% of training data. Now out of the 80% training data, you further divide it into 80-20. You only train over approximately 60% of the data. And then the 20% of the training data you don't touch. So the 20% of the training data you use to evaluate the model at the train time, which will help you prevent overfitting, and you keep on computing the accuracy metrics on that validation data. So you say subset equal to training, seed equal to 1337. So seed is basically some number you give to ensure that the results are reproducible, and we give an image size and batch size. So similarly, we have the validation data set. So val ds we make similar to the train ds. So let us run this. Yeah. So these files, the JPG files, they have the labeled data set with them. So now we will just plot the images. So say here are the 9 images in the training data set. So what we are doing is we are creating a figure, plot.figure fig size equal to 10 cross 10, and for images comma labels. So this will create. So we have this train ds as the data loader. This will basically select one image or one sample from the training data, the images comma labels, and then for I in 1 to 9, so run this, you run this 9 times, and then you say, so you make a subplot of 3 cross 3, and you show the images dot numpy as type uint. So these are the images that are being shown, and then we have the labels. So you can see this. And so if you do train ds dot take one, so you can see that we had the batch size as 32. So a batch size of 32 basically means if you take one sample, so you would extract 32 images. So this images and labels are basically 32 in size. We can check it here as well. So you can see here images dot shape. If you see, so you can see here, it is a tensor of shape 32 cross 180 cross 180 cross 3. So why this 3 is coming is because you have the 3 RGB channels, and then they are using some kind of data augmentation. So saying why when you don't have a large image data set, it's a good practice to artificially introduce sample diversity by applying random yet realistic transformations to the training images, such as random horizontal flipping, some kind of random rotations. This helps expose the model to different aspects of the training data while slowing down overfitting. So they are doing some kind of data augmentation, and then visualizing the augmented images in a similar manner. So you say you take this, you make this data augmentation function and then apply it on the images. So you can see that there is, so they are doing a random flip in the horizontal direction and a random rotation by 0.1 degrees, I think, or radians. So that is what these images are. So some kind of random horizontal shifting and random rotation. Now what they are doing is standardizing the data set. So our image is already in standard size 180 by 180, as they are being yielded as continuous float 32 patches by your data set. However, their RGB channel values are in the range 0 to 255. This is not ideal for a neural network in general. You should seek to make your input values small. Here we will standardize to the values to the range 0 to 1 by using a rescaling layer at the start of our model. So the two options for rescaling are, one is make it a part of the model like this. So you can say you can do, first you are doing a data augmentation, and you are saying, so x is equal to data augmentation input, so then in you will get the augmented data as x, and then you apply, you say x equal to layers, so layers you are getting from Keras dot rescaling 1 by 255. So because in RGB the maximum value of the number, it goes from 0 to 255, and then you apply it on the augmented data. So either you can do this, and then they're saying with this option your data augmentation will happen on the device, and it will benefit from GPU acceleration. So this is a part of the model, and it will go on the GPU, and it will be also be faster as the other model is, because you're running it on the GPU, and it's inactive at the test time. So input samples would be, so during the test time, at the time of testing, you don't have to do any data augmentation, because that's the test data is all you have. And so they're saying that, so the input samples will only be augmented during fit and not while calling evaluate. So dot fit basically does your training. Dot evaluate does your, it basically computes your metrics. It will not train the model. Dot predict will not do the training or evaluation. It will generate your y pred or the predictions. And if you are training on GPU, this is a better option. The second method is to apply it to the dataset so as to obtain a dataset that yields a batch of augmented images. So we will see what to do, and you configure the dataset for performance. So let's make sure to use buffered prefetching. So that, okay, so you basically use this function prefetch. So what prefetch will so when you're training a deep learning model, sometimes even without knowing, you would end in some kind of IO bottleneck. If you are loading a lot of data set even in the same variable, a model will show the hardware will show that your RAM is over. So for that, this if you use the function prefetch and you keep the buffer size as 32 or like some other buffer size, then you can avoid that kind of IO bottleneck. Now we will build our model. So we have seen a small version of exception network. So if you remember yesterday, not yesterday, Wednesday, when we were discussing the models, the different types of convolution, popular convolution neural networks. That time I had shown the inception net. So you can see in an inception net, you have the 1x1 convolution and the different types of convolution in the same layers itself. So similar to inception net, there is something known as exception network. And so they're saying we haven't particularly tried to optimize architecture. If you want to do systematic search, you can consider using Keras tuner. So Keras tuner is for automated tuning of the model architecture. We will see this in the further classes. And so the way you would make the model is, so you say, so you pass the input shape and the number of classes. So this is the output number of classes. So in this case, we have two classes, that is cats and dogs. So this number of classes will be 2. And you say inputs equal to Keras dot. So Keras has got this input function and you have to pass a shape. So what is the shape of the input data? In our case, it is 180 cross 180 cross 3. And then you do a data augmentation. So in this case, they are doing a horizontal shifting and some kind of rotation. And you have this as an entry block. So you do rescaling. Now there is, so you see this, you have this as an input from the Keras dot. So Keras has got this input class. So this input is a object of the input class. Now you pass this input class to the function data augmentation and you get X. And now you keep on moving ahead in the layers. So you output X and you input the same X. So basically saves memory, and then you're using the way the network is constructed. So then there is this class called con2d. So con2d is a class of TensorFlow, or I think of, yeah, for this one, they're using keras.layers.class. We have 32 filters. So the first argument is the number of filters. The second argument is the size of the filter. So this is having a 3x3 size. What is the stride for the filter that is used for this layer? The stride we are using is 2. Now, if you want to keep the size of the input and output as same, you would have to use something known as padding. So we are keeping the padding as same, and we are passing this to the scaled X. Yeah, still there, man. Yeah, so then you would do something called as batch normalization. So batch normalization is within the layer, you would normalize the values back to 0 to 1. It has been found that, like, with different experiments, people have found that batch normalization works really well. So this con2d and batch normalization, this is like the linear combination you do as a first part, and then you do the non-linear activation. So we have the activation class in the layers class of Keras, and you have to pass. So activation class has got different types of activation functions. So you pass the parameter or the argument as relu to this X. So this X is coming from here. So X equal to layers.activation relu X. And then you would do this again. So so after applying 2 layers, you would keep this this saved in a separate variable, so that you can use it, you can use this further as a for residual network or for skip connections. And then you can build other layers with this previous block. So you can say for size in 128, 256, 512, 728. So you will sequentially build the exception network. And then okay, so after doing all these layers, so you would at the end of the class of the network, so you would have to define your activation function. So if it is a classification problem, you would and you are using and you are it's if you are having binary classes, or if you are having two classes, then you have to use the activation as sigmoid. And if you are having multi-class classification problem, let's say you are classifying from numbers from 0 to 1, or there is one fashion MNIST data set, so you're having different number of classes, then you use the activation function as softmax. And then in the final output layer, you use this activation function, and with the particular number of units. So the dense is another class in the layers class of Keras. And what dense basically means is that, so I will, okay, sorry, I will just very quickly show you. Oh, this was dense Keras. Yeah, not this one. Yeah, so you can see that, yeah. So a dense layer is basically if you have a 2D input, and then these are your different convolutions. So dense layer is that when your dense layer starts, you basically flatten your 2D input into a dense layer. So then once the dense layer starts, everything it becomes as a linear, or as, so if you have 180 cross 180, so this will be 180 into 180 number of nodes. So and then the argument of dense gives you so here we are saying units, so that is the number of output, so output that you get from the dense layer. So then you say, okay, so this was your model. And this function make model, what it does is it returns keras.model inputs comma outputs. So you give an input, and then that with that input, so you from this input you make this x, and then you get your output. And this returns your keras.model as a model class. And then you make an object of this model. You say model equal to make underscore model. Now first argument that you have to give here is the input shape. So we give here the input shape as the image size that we had defined. Yeah, we had defined here. So 180 cross 180, 180 comma 180, and then you say image size plus 3. So this is basically for the 3 channels, and then you give the number of classes as 2. So then you also plot, in this case they are also plotting the model. So keras.utils dot plot underscore model. So this is how your model looks. So this has, yeah, if you scroll this, yeah, you can see that in your model you start with an image of size 180 by 180 by 3, and then you are making this sequential input class. You are rescaling your input to you're dividing it by 255, and then you are having a con 2D layer which is having a padding of same. So the input, okay, so this output, yeah, so here the padding is not same, I think. So that is why the output is getting reduced. Oh, yeah, sorry. We are using a stride of 2, so the output is getting, so it's becoming 90 cross 90 from 180 cross 180. And here so then you are doing batch normalization and activation. And then, so then this is the number of filters that is used. So then in another convolution layer, I think we use the stride as 1, or if you don't give the value of stride, so here you see we gave the strides as 2. In this layer we are not giving any value of stride, so the default value is 1, so it assumes, so then the size remains the same, but the number of filters that we must be giving is, okay, so 64. So you can see that from 90 cross 90 cross 32 it became 90 cross 90 cross 64. You do batch normalization, you do activation, and then you save this. So if you remember, we saved this for doing the residual or the skip connection previous block activation. And this one you saved, and okay, so this one we saved and used at different places in the network. So these are the for loops that are running with you can see for, yeah, these loops. So this is the size here, I think, corresponds to the number of filters. Yeah, so 128, 256, 512, 728. So you can see 128, 256, yeah, 512, and then 728. And then you have, at the end, you basically have, we have none comma 1. So in this one, since we are using sigmoid and the units is 1, so as if you remember, I said when you are using a dense layer, the argument you provide to the dense layer, so we provide as 1, so that will be the output. So here they must have provided 4. They're getting 4 nodes. So here we'll have 0 and 1, and then we will have the epochs. So let's say you are having 100 samples. The number of data images is 100. So if you remember, we had a parameter called as batch size. So we divide our data into back into the number of into some groups, and the number of such groups is equal to the batch size. So if you're adding 100 images, and you are having a batch size of 10, then each batch, so it will be divided into 10 batches, and each batch consists of 10 images. And epochs is basically you are running over all the batches for how many number of times. So that is, for 100, if you're having 100 data samples, so you're running 100 samples 50 times. And then we also have something called as callbacks. So Keras has got this callbacks class. So keras.callbacks.model checkpoint, and then you give the name of the model. So what this will do is, at the time of training, it will keep saving the model at a particular epoch. You compile the model, so you say what is the optimizer you want to use. So here we want to use Adam optimizer. We'll see in more detail what Adam optimizer is. The loss we are using is binary cross entropy. This also we will see in further classes in the theory section. And the metrics that we are using is accuracy. So then you compile the model, you say model.fit, you give it the training data set, the epochs argument you have to give epochs equal to the number of epochs. What are the callbacks? So you are saving the model. And what is the validation data set? So validation is at the time of training. You will see the accuracy on the data set for which the model is not being trained, so to prevent overfitting. Yeah, so the training of this model has started. I don't know how much time it takes. This is running on a GPU. So you can see that the binary cross entropy loss is reducing, and the accuracy is increasing. And they say that after training for 50 epochs, we should get somewhere around 96% accuracy. And they also try to run this on some new data set which they don't train the model. Yeah. So I know that a lot of things in this would be sounding maybe something very new to a lot of you, and all these details that we have covered, we will see each of them in much depth in the classes to come. And this is so I wanted to show you an end-to-end example. The more you see examples, such live demos, you'll get more familiar with these libraries and frameworks and the terminology and the theory behind AI and ML. And I think this will take some time to train. So I will yeah shut this down, because yeah, this will take a lot of time. I think it's already we are 45 minutes beyond our official time. So thank you so much for attending this class. And yeah, let me know if you have any questions, or otherwise we can close this session.
Sir, can you share these materials with us?
Yeah, so okay. So what I'm saying is that this this material, the Collab notebook. So I am maintaining just a single presentation, which in which I will keep adding the material. And this is the one that I showed today. This is on the slide number 82 in this image classification from scratch. And you can find this also on the, so this presentation, I am also sharing the YouTube recordings on my channel, so you can see this from there, or you can go to this the repository, and you can, yeah, so I will just change this thing to class presentation. So there will be just a single presentation in which I will keep updating the material. So this class presentation is here, and you can just go there, and on your own also you can just keep doing stuff and then ask me if you face any issues. And yeah, I think so. If desk people are there, can you please stop the recording, because the class is done now. And